So hello students, let us continue our discussion on the Fourier series. So in the previous lecture, uh, we had dealt with the condition of the existence of Fourier series, which is called the Dirichlet conditions. So these conditions were the first condition: over any period the signal must be absolutely integrable, and ft must have finite number of maxima or minima or any finite interval of time. Similarly, third point, the signal must have finite number of discontinuities over any finite interval of time. Let's see the case here. If you see the example number one of this signal, this signal is not integrable. It is not absolutely integrable in the time period in some finite interval. Let's say the signal has a period of 1 second. So this signal is tending towards infinity when it reaches towards 1. That means if you take its integration, its absolute integration from, let's say, 1 to 2, any period, it will tend towards infinity. So for such signals, we cannot represent them in terms of Fourier series. In the second case, although this signal is absolutely integrable, but still this signal cannot be represented in terms of Fourier series representation. Why? Because it has got infinite number of maxima and minima. We will not be able to determine the nature of the signal or the point of the presence of maxima and minima. Hence, likewise, this signal cannot also be represented in terms of Fourier series representation. And third case, the signal must have finite number of discontinuities over any interval of time. We can see this is one discontinuity, this is another. Likewise, there are infinite number of discontinuities are there present in one single period of this signal. Hence, we cannot do the Fourier series representation of such signals. So for any signal that can be represented as a Fourier series summation, it must follow the Dirichlet conditions. Let's see an example of square wave. You can see there is a discontinuity is there at the time instant t naught by 2, but only one discontinuity is present. There are not infinite number of discontinuities present in this signal. In that case, this signal can be represented in terms of Fourier series summation, and it contains odd harmonics. Now, one thing to notice here is that although this signal is discontinuous at these points, see, this square wave has discontinuities. At t naught by 2, t naught, and then 3 t naught by 2. And so on. Similarly at 0 and minus t naught by 2. Now, one thing to notice here is that although this is a discontinuous function, but it is you can see it is a summation of continuous function. The sinusoid is a continuous function. How is it possible that a discontinuous function is a series summation of continuous functions? If you write here, square wave is a Fourier series summation of continuous waves. One thing to also notice is that a Fourier series summation is an infinite summation. It's not that you have done finite series summation, like if you take 100 summations. It's not like that. If you are doing a Fourier series summation, it is 100 summation. Yeah, it is an infinite summation. Then why it is happening that a discontinuous wave is a summation of continuous waves? So, taking the case of the same square wave, suppose we start adding these harmonics from 1 to infinity to obtain a perfect square wave. Suppose we start doing partial summations. Suppose for, let's say, this is the square wave, n equals to 1 to infinity. Let's say for n equals to 1, ft for n equals to 1, so small n, will be given as 4a0 upon pi sine omega naught t. In that case, we will get the fundamental harmonic, which is omega naught. Suppose now we add the third harmonic. That is, now we will do the addition of, we will add two harmonics, one and third harmonic. Then the summation will be 4a0 upon pi sine omega naught t plus 4a0 upon 3 pi sine 3 omega naught t. Once we do a partial summation of two harmonics, the fundamental and the third harmonic, we get the sum something like this. Let's say here, this is a partial summation 50. We are adding the harmonics. We have to do infinite summation in order to get a perfect square wave. What we are doing, we have started adding up all the harmonics, starting from 1, then 3rd, then 5, we will keep on adding. Now suppose we add 7 harmonics, say n equals 1, 3, 5, 7. We are summed up from n equals to 1 to 7, the odd values, 4a0 upon pi. After doing summation from 1 to 7, we have started closely getting a square wave. Still we are not getting a perfect square wave. Similarly, if we do the summation, let's say we have done the summation till the 19th harmonic. Again we are closely reaching to a square wave but not perfect square wave. And let's say we have done the summation, the partial summation up to n equal to 79, let's say up to total 80 harmonics, as in this example. So we can see as we keep on adding the harmonics, we start getting, and we start approximating a square wave. But still you can see the square wave is not a perfect square wave. Some ripples are there at the point of discontinuity. You can see, if we exaggerate here, do something like that. So what is happening is there, initially when we have started adding the signals, the harmonics, the individual harmonics, initially the ripples are present, are uniformly distributed, evenly distributed. Now as we shift from this summation to this point, you see the ripples near the discontinuity, near the points of discontinuity, have started rising. And the ripples in the region of continuity the ripples present in the region of continuity have started to decrease, but at the points of discontinuity, the ripples have started to increase. As you can see, after doing 19 summations, summation up to the 19th harmonic, the square wave is trying to smooth, but at the point of discontinuities, the ripples are increasing. Such that, suppose we have done around 79 summations up to the 79th harmonic. The harmonics, you can see, the harmonics in the continuous region has smoothened out. Or you can say the ripples have shifted towards the discontinuity, point of discontinuities. Once again, drawing this signal here, this is the figure, or this is the graph of the square wave after 79 summations. N equals to 79. That means we have done the summation from n equal to 1 to 79. One thing to observe here that the region of continuity, these are the regions of continuity. And these are the points of discontinuity. So likewise, as we keep on doing partial summations, what will happen? The ripples will shift towards the discontinuity. Okay, write here one point. As we keep on doing partial summations, the ripples shift towards points of discontinuity. And practically it was found out that the peak value of the ripples is always 1.09 times the peak amplitude of the wave ft. And this phenomenon is called Gibbs phenomenon. Two points, as we keep on doing partial summations, like suppose we represent ft in terms of partial summation, let us write here n, where n equals to 1 to capital N, and for square wave it is where n represents partial summation up to nth harmonic. So the thing is that as long as n is a finite value, there will be ripples in the wave. In order to get a perfect square wave, one should sum till n tends to infinity. So in order to get a perfect square wave, we have to do a total summation, because ft, suppose ft is represented from n equals to 1 to infinity 4 a naught upon n pi sin n omega naught t, or in the second case we write n equals to 1 to capital N, will do partial summation. This is total summation. And suppose we are doing partial summation. where let's say n is a finite value, or n less than infinity, n is a finite value. In that case, we will get ripples. Ripples of peak amplitude (1.09 times of peak value of wave. And this phenomenon is called Gibbs phenomenon. So the purpose of the discussion is that we need to do infinite summation in order to get a perfect Fourier series expansion or the perfect curve of the wave. Otherwise, there will be ripples in the wave, or the wave will be of a distorted nature. Next point is orthogonality of Fourier series. Suppose there are two signals x1t, and let's say there is another signal x2t. So their inner product suppose its time period is fundamental time period is t1, its fundamental time period is t2. Then its inner product x1t dot x2t is given as 1 upon t x1t integration over the time period multiplied by the conjugate of x2t, or you can interchangeably write x2t into x1t conjugate to dt, where t is the LCM of t1 and t2. So this is called the inner product between two signals. It is similar, suppose we have two vectors, let's say A and B, and let the angle between them is 90 degree. So we know that if we take the dot product, if it will be equal to 0, and suppose they have the angle between them is theta, suppose we are taking the dot product, then it will be non-zero and will be equal to cos theta only. because A and B are unit vectors. Let's say they are unit vectors. So when the angle between them is 90°, in that case the two vectors are orthogonal. In the same way, if the two signals have an inner product equal to inner product as 0, then these two signals are called orthogonal signals, or they are orthogonal to each other. So we can write two signals are orthogonal if their inner product is 0. Now let us take the case of Fourier series summation. Once again writing the inner product between two signals x1t, x2t is given as 1 upon t multiplied by x2t conjugate t. Now if we are taking the inner product of the signal with respect to itself, let's say x1t equals to x2t, same signal only we are trying to take its inner product with respect to itself, let's say is equal to xt, then its inner product will be given as 1 upon t, that will be xt multiplied by xt conjugate, and this will be equal to mod of xt dt xt square. So this is nothing but the average power of the signal, average power of xt. So if we take the inner product of the signal with respect to itself, then that inner product represents the average power of the signal. Let's say we represent any signal as Fourier series summation. Now this you can see ft is a sum of it is an infinite summation of sinusoid, so many other signals like c0 plus c1 e to the power j omega naught t plus c2 e to the power j 2 omega naught t. Likewise till infinity, and same case for negative plus minus. Now let us consider any two harmonics randomly, any two harmonics, and let's name them as k omega naught and l omega naught. That means in that case, let's say x1t, we have two signals x1t, that will be ck e to the power j k omega naught t, and the other signal will be x2t cl e to the power j l omega naught t. Let's try to take its inner product. Then x1t dot x2t will be given as 1 upon t, where t will be the fundamental period of the signal. It will be x1t into x2 conjugate of t dt 1 upon t naught 0 to t naught. x1 is given as ck e to the power j n omega naught t, k omega naught t, k omega naught t, and multiplied by the conjugate, so it will be cl conjugate into e to the power minus j l omega naught t dt. Further, this can be written as t naught into this is L into e to the power j minus L minus k omega naught t into dt. Now it will have two values. Suppose if L equals to k, then this term will go 0, then its value will be simply ck into cl. Now since we are taking L equals to k, this will be, let's say L is equal to k, and let's say it equals to m. Then putting k is equal to L, this can simply be written as cm square and for L not equal to k, we know that this integration will be 0, this value will be 0. So when L is equal to k, it represents, when L will be equal to k, it represents same harmonic. That means x1 equals to x1 equals to x2. Then if we take xt, xk into xlt, so its inner product will be for L is equal to k, that means for the same signal, or for the same harmonic m omega naught, and for L not equal to k for different harmonics, is 0. So you can see that for different harmonics, since their inner product is 0, that means they are orthogonal. We can write here two harmonics of we can simply write here two harmonics are orthogonal to each other, any two harmonics, because since we are choosing arbitrary values of k and L, we can say that any two harmonics are orthogonal to each other. Second here you can see, if we are taking the inner product of the same signal with respect to suppose we are choosing an mth harmonic and we are finding its inner product, and we know that the inner product of the signal with respect to itself represents the average power of the signal. That is why we can say that for the same signal, let's say we take the dot product, the signal with respect to itself, it will be equal to the average power of the mth harmonic, it will be equal to Cn square. That means we can see for any mth harmonic present in the signal, its average power will be equal to the square of the magnitude of the corresponding Fourier series coefficient. We can write in general, if we want to write the average power of nth harmonic will be equal to Cn square. Now the average power of nth harmonic is given as square of the magnitude of the Fourier series coefficient. Now since there are infinite number of harmonics present in the Fourier series summation and the signal is the sum of those harmonics, then the total power or the total average power of signal ft will be given as will be equal to summation of minus minus infinity to infinity. And this is called Parseval's theorem. Which is the total power contained in any periodic signal equals to the total summation of the square of Fourier squares of Fourier series coefficient. This is called Parseval's theorem. Let us see the same example of square wave. Suppose this is our square wave. And let's say its magnitude is peak value is plus a0 and minus a0. And we know its Fourier series expansion as summation n equals to 1 to infinity 4 a0 upon n pi sine n omega naught t. Now if you want to represent this in the exponential form, only odd values n equals to minus infinity to infinity. Now we know this is the value of Bn. In that case, now we know that Cn is equal to minus j Bn by 2, which is minus j by 2 4 a0 upon n pi. So mod of Cn will be two a0 upon n pi. Similarly, C minus n, its magnitude will be the same, 2a0 upon n pi. So, the total power contained in signal Ft, which will be given as, according to Parseval's theorem, square of the summation, total summation of the square of the Fourier series coefficients equals to minus infinity to infinity, only odd values. It will be equal to 2 times of the summation because of the symmetry, because Cn and C minus n are the same. Now, if we solve it, it will be 2 times of summation, and this will be 2a0 upon n pi whole square, n equals to 1 to infinity. It will be, if we take that 2a0 upon pi outside, it will be 4, 2 into 4 into a0 square upon pi square, it will be 1 plus 1 by 3 square plus 1 by pi square, because the square wave only contains the odd harmonics, and so on up to infinity. this value is pi square by 8. Please refer to the mathematical concept regarding the summation. This value will get close to pi square by 8. Then thusly 8 into 8 now a naught upon pi square into pi square by 8. Its value will be a naught square only. So with the help of the Parseval's theorem, the average power contained in the squared signal is given as a naught square. We can directly verify this, since we already know that the average power of any signal is given by the square of its RMS value, any power signal. So now we know that its RMS value will be a naught only, that is a naught square. Same thing we have found out with the help of Parseval's theorem. One more thing to discuss here is the half-wave symmetry. A signal is called half-wave symmetric. Suppose there is a signal ft whose fundamental time period and frequencies are omega naught t naught. So this signal will be called half-wave symmetric if the signal ft equals to minus ft t plus minus t naught by 2. This is the condition of half-wave symmetry. For example, let's take the example of the square wave. Let's say it's a naught minus a naught. Let us shift and inverse the signal. Do the shifting. This is t naught by 2. This is t naught. Let us do the shifting. It will be somewhat like, if we do the shifting by t naught by 2, the wave will become and then do the inversion minus f t minus t naught by 2. If you invert this, you will again get the same signal. Right here on this. Once again you got the same signal only. Hence the square signal is a half-wave symmetric signal. Another example you can see is a triangular wave. This is also an example of half-wave symmetric signal. Now, what is the peculiar thing about the half-wave symmetric signal is that the half-wave symmetric signals contain only odd harmonics. Odd harmonic means, suppose the fundamental harmonics omega naught, then 3 omega naught, 5 omega naught, such like that, only odd harmonics. You can see how, suppose ft signal is represented in terms of Fourier summation. Then we can see its Fourier series coefficient is given up as Cn. Suppose we want to write the Fourier series summation of t plus minus t naught by 2. Let's say it is given as c dash n e to the power j n omega naught t. Now, in that case, c dash n can be written as ft plus minus t naught by 2 e to the power j n omega naught t dt. Let's say tau equals to t plus minus t naught by 2. Putting these values here, we can write, and you can see d tau will be equals to dt only, and t will be equals to tau minus plus t naught by 2. Then Cn can be written as 1 upon t naught integration, and for t is equal to 0, its value will be minus plus t naught by 2, and similarly for t naught it will be t naught minus plus t naught by 2, and it will be f tau into e to the power minus j n omega naught this will be plus minus. So it will be tau minus plus t naught by 2 into d tau. Taking t naught by 2 outside, you can write, and let's do the integration minus, because there should be minus, because what we have considered, ft must be equal to minus ft plus minus t naught by 2. Then do minus here, and then minus. Taking t naught by 2 outside, we can write minus e to the power minus j n omega naught, and this will become plus minus t naught by 2 integration plus minus t naught by 2 to t naught plus minus t naught by 2 f tau e to the power minus j n omega naught tau into d tau upon t naught. Then we can write Cn dash equals to minus e to the power plus minus j, and you see this value is 2 pi. So this will be Jn pi into 1 upon T naught e to the power integration e to the power minus j n omega naught tau into f tau d tau. Now this is nothing but Cn only. That means C dash n equals to minus e to the power plus minus j n pi to Cn. Now in order to make, since we know that since for a half wave symmetric signal ft must be equal to minus ft plus minus t naught by 2, and ft has a Fourier series coefficient of Cn and this has a Fourier series coefficient of C dash n. Since both these signals are equal, then a corresponding C dash n must also be equal to Cn. In that case, this particular term must be equal to 1. Then we can write C dash equals to minus e to the power minus plus minus j n. Now its value will be equal to 1, n is equal to odd, and its value will be minus Cn when n equals to. For a half wave symmetric signal, C dash n must be equal to Cn. That is why this case is, we cannot take the value of n is equal to even. The only value that we are left with is C dash n equal to Cn for n equal to odd. Hence we can say for a half symmetric signal we can only odd hierarchies. We will continue our discussion on Fourier series. Thank you.